Now that we've looked at inverse functions, I want to talk about solving radical equations. Radical equations are equations that involve radicals or exponents that are fractions. So we want to be able to solve equations like this. In other words, we're looking for all of the values of x that we could plug in that would satisfy this equation. Now, if you wanted to solve an equation like this, our first goal is going to be to isolate any radical expression. So we want to get that radical expression by itself. And to do that, we'll follow the usual strategy that we would whenever we're trying to isolate some variable in a linear equation. So in this example, I would want to add 2 to both sides of the equation just to get that radical by itself. So I would get that the square root of x plus 5 is equal to 3. And now to get rid of a radical, what we're going to do is the same thing that we've been doing with these exponential and logarithmic equations. So what we do is if we are trying to kill something like a square root here, then we would apply its inverse function to both sides of the equation. So in this case, it's relatively simple. All that we're going to do is we'll square both sides, because I know that the inverse function of the square root is the square. So on the left side, these will cancel, and I'll be left with just the original input, x plus 5. And on the right side, I get a 3 squared, which is 9. And now the resulting equation is just a normal linear equation, so I can solve this by just subtracting 5 from both sides. I get that x is equal to 4. Now, in these problems, whenever you apply an even power to both sides, you unfortunately need to check whether this solution actually does work in the original equation. So I need to come back up and check x equals 4 in the original equation. That would give me the square root of 4 plus 5 minus 2 is supposed to be 1. What I like to do is put a little question mark above the equal sign if I'm just checking that these two sides are balanced, but you can also just evaluate each side separately. And then on the left side, what we have is a square root of 9, which is 3, minus a 2 equals 1, and this does indeed work. So that means that our solution in this case is x equals 4. So sometimes in these problems, you'll end up getting solutions that don't quite work in the original equation, and therefore you just toss out those solutions. But this strategy that we're talking through here will find all of the candidates for the solutions. So it'll find all possible solutions. We just might need to throw out some of them. Notice that in this problem, I could have thought of that square root as a fractional power. So I could have written this as a 1/2 power. This is just a rewriting of the original equation. And in this case, the strategy is still the same. So we still want to isolate the radical expression, or the expression that has a rational exponent. But notice that the power that we applied to cancel a square root earlier was a positive 2 power to both sides. The thing that I want to point out about these rational powers is that if you want to kill a 1/2 power, then what you need to do is raise both sides to its reciprocal power. So in other words, if I wanted to kill a 1/2 power, what I could do is I could raise both sides to the 2/1 power, because then whenever I repeat exponentiation here, those would be cancelative. So then I would just end up getting x plus 5 on the left side. Similarly, over here, I would have 3 to the 2/1 power. So that's just sort of a fancy way of rewriting what we did above in terms of this reciprocal power. But either way, we end up getting the same equation that we did before. We would get x plus 5 is equal to 9. So let's look at one more example involving some more complicated rational exponents. So let's say that I have something like x to the 3/5 minus 6 is equal to 2. Now again, if I'm trying to get at x here, I want to first isolate this expression that has the rational exponent, and then I'll worry about killing that rational exponent. So I would add 6 to both sides here, then I would get x to the 3/5 is equal to 8. And now to kill a 3/5 exponent, I can do the same thing that I did just before this problem, where I look at this exponent and I raise both sides to the reciprocal exponent, because that will be the inverse function of the 3/5 power. So the function that I would apply to both sides would be raising that side, or raising each side, I should say, to the reciprocal power 5/3. So I'll raise both sides to the 5/3 power. Now the reason for doing that is that on the left-hand side, remember that when I repeat exponentiation, I would be multiplying. So I would get 3/5 times 5/3. Those would cancel and leave me with just a single power, or x to the first power. And then on this side, what I have is 8 to the 5/3. This I can actually simplify a little bit. You can think of this as 8 to the 5th power with a cube root attached to it, because remember this exponent says to raise to the 5th power and take a cube root. You can treat it that way, or you can treat it like the cube root of 8 first and then raise it to the 5th power. In other words, you can do either of these operations in either order. So you can do the 5th power first, or you can do the cube root first. I would recommend that you do the fractional part first, or the denominator part first. In other words, take the root first, because it'll keep the numbers a little bit smaller. So here I would have to compute 8 to the 5th power, which is gigantic, and then I would have to take a cube root of that, which is kind of irritating. Instead, what I can do is I can take the root first, which would be the 3rd root of 8, so that's 2. And then after that, I can raise to the 5th power. So what we'll end up getting is 2 to the 5th, which is 32. Now in this example, we didn't raise anything to an even power, so I don't actually have to check this answer. When you don't use even powers on both sides of the equation, then this solution is guaranteed to work. The only ones that you really need to check are the ones where you raise both